of you know who I am. I'm Reason, one of the co-founders of Repair Biotechnologies. Logo and name right in front of you. Not too hard to guess that. In any case, I'd like to talk to you today a little bit about what we're up to at Repair. I think some of our recent data is very promising, and I hope you'll find it just as exciting as I do. So before proceeding, I should say that if you take one thing away from you from listening to me ramble on about all the fascinating stuff we're doing, you should take away repair, that one word. If you're going to do something about aging, then you had better be able to articulate quite clearly how and what you are repairing. Aging is a matter of damage and dysfunction, and if you're not able to say that you're quite clearly repairing something, then you're probably not doing a great deal of good. And I wish more people would see things that way. So for those of you who don't remember, Repair is primarily working on what we call the cholesterol degrading platform. We're at a preclinical stage with this exercise. What this is a entirely first-in-class, very novel approach to therapy that is aimed firstly at reversing atherosclerosis, a condition that kills everybody who doesn't die from anything else. And then familial hypercholesterolemias that are forms of accelerated atherosclerosis. But in principle, any condition where there is too much cholesterol somewhere in your body is prone to being treated by this sort of approach. What we do is, in effect, provide cells with the ability to degrade cholesterol. And this is very powerful precisely because the human body does not do this. The human body is very good at moving cholesterol around and making it and excreting it, but it doesn't degrade it in situ. So it's a very interesting approach to take. And we've demonstrated this last year that it works, and it's quite well tolerated in mice. In fact, it doesn't appear to do them any harm at all. So based on this, we hope to begin clinical trials in 2022 if everything goes swimmingly. And specifically what we're looking at, we would like to enable macrophages to perform this clever trick of breaking down cholesterol, because macrophages are the problem children in atherosclerosis, a disease that kills between 10 and 25% of everybody, depending on how you count. And yes, there are well-used treatments for atherosclerosis, and I'll get to that in a bit. There are also these two very, very useful, unless you happen to be a patient who suffers from it, orphan disease, or sort of genetic diseases, one of which is an orphan, which is heterozygous familial hypercholesterolemia, HeFH, and homozygous familial hypercholesterolemia. The heterozygous, you only have one copy of your gene mutated. The homozygous, you have both copies mutated, and you're in much more trouble. In those cases, these people, these unfortunate patients, have very, very high levels of blood cholesterol, which greatly accelerates atherosclerosis, and their condition is frequently discovered far too late, and as a consequence, they die young. We also have a number of other cell types and indications that we, alas, cannot talk about at this point in time because we're very busy engaged in patenting. One of the sad facts of running a biotech startup is that the further you go, the less you can say to people. It's, I realize, slightly frustrating to those of us outside, but it is what it is. Hopefully we'll be able to talk about these early next year, and they're very, very interesting indeed. But atherosclerosis and the accelerated forms. So in essence, what happens here is there's too much cholesterol, and you get as a result the buildup of fatty deposits that narrow and weaken your blood vessels, and ultimately your blood vessels just explode or get blocked, and you have a heart attack or a stroke and you die. 10 to 25% of everybody. So at the moment, the best we can do are these statins, PCSK9 inhibitors that essentially lower cholesterol in the bloodstream. And this slows it down by sort of 20% or so, which is, okay, better than nothing. But really, in the grand scheme of things, this is not great. I mean, if you have cancer and somebody says, hey, we're going to slow your cancer down by 20%, you know, that's not really what people want. What we want is a cure. There's no amount of lowering of blood cholesterol that will stop atherosclerosis from killing you. It's these plaques are in fact essentially macrophage graveyards, because macrophages are the cells that keep blood vessels clear of this stuff. But as you grow older, you get more forms of cholesterol that macrophages can't handle. and they become pathological, inflammatory, and eventually die. So an atheroma, the plaque, is a macrophage graveyard in which the dying and dead macrophages are releasing signals that call in more macrophages. It's a feedback loop. Once you have the plaque, you're going to die. It's just a matter of time. So we need to do something about this. We need to break down the plaque. We need to get rid of it. We need to get rid of the cholesterols that are in the plaque, make the macrophages happy again, and really actually reverse the disease. This is the holy grail of atherosclerosis research, and not something you can achieve with statins, PCSK9 inhibitors, and other things that reduce blood cholesterol. You need a new and radical approach. So I find often that I say all that, and then people say, well, what do you really actually mean? You're going to reverse the plaque. So we put together this prospective, this is the aspirational view of what we'd like to do, which makes more sense to some people. Here we have the untreated folk just die at some point, whereas people with statins are going to die more slowly, less early. But it's still not great. 20% reduction in mortality, 10% reduction in plaque volume. This is not the way to a cure. What we want, what a cure is going to do, is literally reverse the plaque, reverse the mortality, get rid of the disease, act as a cure. And if you take it early enough, you will never get the disease in the first place. People in their 40s, as the recent studies have shown, have measurable plaque in many cases. Some large fraction of people in their 40s have enough plaque to be seen on imaging. Not good. So with that said, what about the science? So this is a pretty picture, and we like showing this pretty picture. It shows a bunch of transfected macrophages showing very robust expression of our CDP throughout the cell. And when we can do that, what you see is the CDP is basically breaking down cholesterol into its catabolite, which can be removed from cells and excreted quite quickly and broken down elsewhere in the body. So you have these 293Ts, which are workhorse cells, showing that we get 20 times as much of the catabolite as is normally generated just by putting this in there. And the U937s on the right there are a sort of workhorse human macrophage line, showing that we can do just as well there. Basic proof of function. Now, function is great, but is it toxic? That's the primary question that you should always be asking yourself. And here, what we are showing is, in fact, it really doesn't appear to be toxic to cells at all. These are cell cultures, and you're checking cell death rate. And these cell death rates are totally normal for cultures under conditions where we're exposing the cells to various forms of cholesterol, LDL cholesterol, acetylated LDL, oxidized LDL, that sort of thing, PBS being a control, of course. Totally normal levels of cell death, no more toxic than the other. So that's great, looks safe so far. Now, this is a more interesting demonstration. Foam cells are what happens to macrophages when they get really messed up by cholesterol. They become these things on the left here, where you have the green is lipid droplets. The cells become packed with them because they're so pathological and dysfunctional that they can't get rid of the lipids at all. They can't export them anymore. They just blob around being horribly inflammatory and die. On the right is the same type of cell, but expressing our CDP in red. And you can see that the ones that express CDP are not foam cells, whereas the few that were unlucky enough in this culture not to express CDP are not doing so well at all. And the bottom right there and bottom left, a couple of non-CDP expressing cells are becoming very foamy. So this is a great thing to be able to show. You want to be able to show that you can prevent and reverse foam cell formation, because foam cells are really the big problem children in atherosclerosis. They're doing the lion's share of the damage by hanging out in plaques and just messing the place up. But great, okay, so you can do this in cells. What about in animals? So this is really, really great data, I should preface by saying. Let me explain it. On the left here, we have 7 control mice. On the right, 7 treated mice. The red staining here, these are cross sections of the aortic root. You can actually see the leaflets in the middle here if you look closely. The red staining is plaque. It's the atherosclerotic lesion. And you can see just eyeballing it. On the left, the control mice are way worse off than the treated mice. What we did here is we took a normal mouse model for atherosclerosis, let it grow plaques in the mice here, control and treatment for a while. Then we gave them one treatment with the CDP therapy. Then we waited a few weeks and saw what happened. So what happened here is that the plaques were reversed. And you can see on the right by about 42% in cross-sectional area, which is a really good result. This is up there with the best that's ever been done in mice. And we did this with an unoptimized first hack at putting this in mice. We will do a lot better once we've optimized this, I would expect. So this is very exciting. This shows that this works, that we can reverse atherosclerosis in mice. And from here, we hope to do good things. So the market size for atherosclerosis is enormous. We will likely go do an orphan indication first because that's much easier to go through the process. And since the orphan indication in this place is literally accelerated atherosclerosis, by being able to effectively reverse homozygous familial hypercholesterolemia atherosclerosis, we also show that we can reverse the normal atherosclerosis. For us, it doesn't matter how the plaque is generated at all. It matters that it's there and that we can reverse it. So what we hope to do here is generate a universal macrophage cell therapy. What does that mean? So what one does there is one would generate a line of macrophages from probably induced pluripotent stem cells. One would then remove such items as the major histocompatibility complex from that line such that these cells don't trigger the immune system of people they're put into. Then you make them express CDP. At that point, you have cells that you can just put into a body, anybody's body. They can be very well quality controlled, made very safe. You can even get them suicide genes so you can kill them if there's a problem. And then put them in people's bodies, and these macrophages will home to areas of damage in your blood vessels and do their work there. And that should hopefully reverse atherosclerosis quite effectively. This is not a very novel idea. A lot of people are working on universal cell lines of various sorts, including our friends Ajax, I should say. And macrophage therapies are not unusual either. There's been a couple of trials of people putting macrophages into humans to address various conditions and show that those macrophages do in fact home to areas of damage such as stroke lesions. So this is all great. And of course, we have to point out that we also have things we can't tell you about that are quite interesting. More on that later. So I should wrap up here by showing you a recent group photo of the lab team in Syracuse who's been working hard at this for the last year and who are making this all possible. Mark, Garrett, and David, led by Morad, are doing enormously great work as Bill and I hack away at the business side of the business. So with that, I will wrap it up here and say, watch this space. I feel that we've proved our point that we can do this, and exciting things are going to happen in the year ahead. Thank you all.